Okay, so hopefully you all have ordered something from Amazon or failing that, some other online retailer at some point in your lives. So you know the basic process, right? You go to the site, you browse around, you add some things to your cart. Eventually you say, I've got enough stuff or I've run out of money. I check out. When you're checking out, you select some delivery options like what kind of shipping you want and where it's going to get shipped to, whether you want it gift wrapped, whatever. And then you pay, right? That's the process. We know this. Okay, so that's what we see. That's the front end. The front end is all the stuff that the customer sees. The back end is all the stuff that goes on at Amazon, right? The stuff behind the scenes. So with that, a whole bunch of different systems got to work together to process the order, right? Some of them are internal, like if Amazon is doing its own shipping, it's got to send notes to its own people, or if it's sending it through UPS or FedEx, it's got to let them know, hey, we got one more thing for you to throw on your truck, okay? And then there's a whole bunch of database activity. Amazon's got to record that there's money coming in and that somebody bought something and maybe it's time to reorder it. All sorts of little things like that going on behind the scenes, okay? So, things like inventory management, right? Checking if you have it. Holding on to something, making sure that nobody can buy that thing. Suppose there's only one left in stock, or it's from a third-party vendor. Amazon's got to make sure that nobody else is coming along and buying that while the transaction is pending, right? And then any updates to the information. For example, again, third-party vendor selling through Amazon. Amazon's got to send a note to that person saying, hey, somebody bought your thing. Do what you will with that information. Okay, credit card stuff. Supply chain coordination, figuring out what truck the thing is going to go on, what sort of shipping model, how it's going to get packed, all sorts of things like that. Okay. So, you don't need to memorize these, but this is just, to understand there's a lot of stuff going on behind the scenes. Okay? All right, and these are, examples of the sort of things that happen. So, a little bit more detail. Generally speaking, when somebody comes along and adds something into their shopping cart at Amazon, the items that get placed in the cart are probably locked. Okay? It's not a guarantee that it happens with all things all the time, but typically, a shopping cart is basically a virtual version of a real shopping cart. And if you're going around through the store, right, through a physical store, and you take something off the shelf and you put it in your cart, you don't want somebody else to come along and say, hey, that looks nice, and reach into your cart and grab it from you, right? Especially not if it's like, the hot toy at Christmas and, there's only 5 of them in the store and you were one of the lucky ones to get one. Yeah, so Amazon's got to manage that. And that's what we mean by locked, is basically saying it is in your cart. Nobody else can access this data to try to buy it, right? Nobody else can add that item to their cart. So when you get checked out, what happens? Well, if your credit card number gets validated, you see if there's enough money in it, and the payment gets processed. There's also some fraud detection mechanism. Some of that's probably happening at Amazon. Some of it's probably happening at the credit card company. Okay? And if the checkout fails for whatever reason, right? If there's like some kind of transaction failure, you say, oh, your card is maxed out, you can't use it, or it trips some fraud detection alarm like, oh, I can't believe you're ordering 1,000 diamond rings and sending them to an address in another country that you have no prior affiliation with. Okay? Something like that. Then those items might get unlocked and be available to other people. Okay? If the warehouse, wherever it may be, receives the order request, and remember, Amazon's a big operation, right? They got warehouses all around the world. So you go to the website, you buy something, wherever that website is hosted, the server where that's running in, it's probably not the same physical location as the warehouse, right? Chances are. Delivery arrangements get made, whatever needs to happen there. And the inventory levels get updated. Say, okay, we have this thing, but basically it's for purposes of inventory, we don't really have it anymore. Somebody else has put a claim on it. It's not in the warehouse. It's on a truck going to the customer now. Okay, so all that kind of stuff. Now, within a transaction, it's very important that the sequence of data updates happens properly. For example, things that could go wrong. The inventory updates before the credit card gets validated, right? You don't want that to happen. You don't want, all this inventory stuff to happen, notifying FedEx, hey, we got a thing for you, and then a second later you're like, oh wait, credit card didn't go through, sorry, forget it, never mind, cancel that, right? You don't want that to happen. Other kinds of supply chain updates before the payment receipt comes in, right? So even if, both inventory and supply chain. So you want to make sure that it gets paid for before it goes, and you want to make sure that you've contracted who the shipper is before you say, oh, you have a thing, right? You don't send note out to all your possible shippers before you figure out which one. So the way they work, every process step happens as a unit. It might involve a bunch of related operations. For example, this credit card transaction, the one part of it is checking if the balance is okay, but another thing is doing the fraud detection, right? And another thing is confirming that, the address is usable, because sometimes there can be a little bit of a snag where if you use a totally new address, there's an extra level of scrutiny on that. So that whole thing, right, is one unit. Do we have a valid transaction? Once you have that, then you can proceed to the next steps, right? Figuring out who's going to ship it. Once you've confirmed that the shipment is going to happen, then you can actually go ahead and deduct it from inventory, right? Because until you have a shipper for it, there's not much point in saying, oh, we have one less thing. So every one of those process steps either succeeds and thus enables the next step, right? Whatever the step in the sequence is, or it fails, at which point, you can either abort the whole process. You can say, nope, this transaction isn't going through, right? Like if a fraud detection flag happens, that might cancel it. Or if the credit card is maxed out, that might cancel it. Okay. So, now in principle, like we talked about with ACID properties, it's a bad idea to let multiple users have access to the same data at the same time. One problem that can happen is what are called dirty reads, right? Where basically a change has happened to the data while another person is looking at it, and so the data that person has would be different. Draw a picture, very quick picture. It doesn't need much explanation, right? So suppose you have data, whatever it is, say number of items on hand. Have you guys heard of Buttheads? Not Beavis and Butthead, but Butthead's the kid's toy? No? All right, so we're going to do a little detour, because this was like the hot Christmas thing last year. With the tagline, Buttheads, their heads are butts. So, Buttheads, their heads. All right, so this was an actual commercial we saw when we were watching some shit with our kids one night. And turn on the sound here. There we go. You get the idea. Buttheads, their heads are butts. So, anyway, so we're selling buttheads, right? So, how many buttheads in stock? Okay? And suppose one person is looking at it and there's actually only one, well, let's say we're buying robot, okay? There's only one robot left. So an example of a dirty read would be, I look at the site, at the page, and see there's one left. Okay, so that's step one. Okay, step two, person number two looks at the page and also sees one left, okay? And as far as that goes, there's no problem, right? At this moment in time, we're both looking at the same page, we both see there's one left. That's okay. All right, but step three, I buy it, okay? And unless there's something else going on there, right, where there's some sort of automatic update to refresh the page, this person is going to see information that is no longer true. Yeah? So this is a problem. This is a basic problem with ACID type stuff, is that in a retail site, something as big as Amazon, you want multiple people to be able to look at a product page, right, and see how many are in stock. But once somebody buys something, the information about how many are in stock is going to change. And so, you know, this guy might be looking at the page saying, oh, there's still one left, it's fine. But he's a little slow on the draw to get it. And when he clicks, it's not there anymore, okay? That's a simple example of a dirty read. You can have, you know, obviously more complicated, more significant ones, but just the idea is the data one person is seeing is not really what's there. Simple. Another thing, imagine if there are two copies of data somewhere, right? So what would be an example of that? Suppose you've replicated your database so that your work center in London has one copy and your work center in Chicago has another, okay? And somebody's trying to look at some version of a document. So person A in Chicago looks at it, makes some changes, and while the replication process is going on, before the replication actually happens, somebody in London tries to look at the same document, but a different replicated copy over there, and doesn't see that the changes have happened yet. Even though the changes have happened, they haven't replicated in time. So this is the idea. Multiple people, in principle, looking at the same data, they can see different things if the system doesn't update basically instantly. But if you enforce that everything has to be updated instantly, then the whole system slows down. So there's a problem with the trade-off. Okay, so at Amazon's rate, right, several hundred transactions per second, and that's just baseline. That's like normal activity. Some things are necessarily going to overlap. Some people are going to be looking at the same data at various times. So the resolution options, the way you can handle that, number one, you could throttle the transaction rate. But that's not practical. That means basically everybody's going to have to wait. You don't want everybody to have to wait to run their transactions through or to look at any piece of data that's on a page. That would be bad. Another thing you could do is you could splinter the operation. For example, suppose you have a separate page that gets generated for any possible item of a category, right? So like basically for every separate butthead toy in stock you have a separate web page for that. And then you say either this one is in stock or it isn't. That would work, but it's kind of a hassle if people want to buy multiple things, because then they have to go to, if they want to buy 12 of them, they're having like a Christmas party and they want to buy one for every kid, they have to go to 12 different pages to do that. Kind of a hassle. So sometimes that can work, but a lot of times it's not really something you want to do either. The other one is to permit some simultaneous data access. And the basic idea here is if the consequences are trivial, then yeah, let people look at it at the same time, right? If you're not talking about, Bitcoin and somebody running off with $20 million worth of Bitcoin in a hack, yeah, then that's okay. If the only, if the only problem that you could see is basically in this case, the consequences are pretty trivial. So, automatic update to page, possible but unlikely that this person might not see the notification before trying to add it to cart. Okay, this is one of those things that we expect. Okay, I go to a website. If it says there's only one left, we understand there's a possibility that somebody else might be looking at it and grab it, right? It would be unfortunate. It would be annoying, but we can see this happening and there's not much to be done about it. Also, Amazon updates the information pretty quickly, right? I mean, it's not like microsecond instantly, but if I buy it, there's going to be a notification that goes out to other things in the system. And that part of the page will get uploaded. There's a technology called Ajax that basically allows that sort of automatic partial page refreshing. So it's possible, but unlikely that the problem is going to happen. And even if the problem does happen, the consequences are not severe. The person is going to be, dang, I got to go somewhere else and buy my butthead. Okay? All right. Yes? That is a good one. That is a good example. So you guys have done Ticketmaster, right? Well, I mean, it's better than having to go to the place in person and buy a ticket. Yeah, but yeah, I mean, yeah, it has its annoyances. The basic thing with Ticketmaster, right? You pick your venue, and then you pick your section, and then it offers you a few tickets from that section, right? More or less randomly generated. And you accept them or you don't, but you have a little window of time to do it, right? And so while they're there, in effect, they're in your shopping cart and you have the option to keep them or not. But they're locked for like a few minutes while you make the decision, right? Because again, in that case, it would be super annoying if you say, oh, look, I get front row tickets, right? And I randomly got front row tickets, but I didn't press, whatever fast enough and some other dickhead bought them out from under me, right? That would be considered a big problem. The other problem with something like Ticketmaster is if somebody out there was just a total asshat and they went to the concert venue, the site, and they ran a script that said, pick all the tickets, but then they just let them sit in their cart and didn't let anybody buy them, right? So it kind of has to have until after the concert was over. So they have to strike that balance where they give people a reasonable amount of time where they're exclusively theirs, but then they have to release them back to the pool because, again, otherwise some dickhead's going to come along and do that. Yeah, there's a certain category of people that it seems their mission in life is to shit in the punch bowl at parties, right? Yeah. Anyway, okay? So, things that can go wrong, multiple users simultaneously. What if somebody attempts to buy the same last item? It could happen, it's annoying, but most of the time not that big of a deal, and people expect that could happen. On the other hand, what if two people try to use the same gift card? That's potentially significant, right? Because they can scam Amazon for money. And if they can have two people using the same gift card, who's to say they couldn't run a script that has 1,000 people using the same gift card? And who's to say they couldn't run that script 1,000 times a day to have 1,000 people use the same gift card, right? So if it involves, information that's not really cash, it's usually not that big of a deal. If it does involve digital cash, has to be super secure with that, and that stuff really has to happen sequentially and in isolation. You want to make sure that a gift card transaction, once that gift card number gets entered into the system, nothing else can use that same gift card. So you basically have some kind of governor over the entire system that there's an approval process in a sense. There's like a manager in your system that says, you're using a gift card? Great. Nobody else can use that gift card, and any, other gift card checks will have to come through me. Does that make sense? Makes enough sense. Okay. So, practical solution to this, partial solution is locking. So, like I said, if one user is using a particular thing, it's locked so that nobody else can use it. So, in the case of Ticketmaster, right, those potential tickets, they're temporarily only yours in the sense that only you have the opportunity to buy them for a couple minutes. If you're using a gift card, that gift card can only be used by you in that interval of time, right? So while that transaction is pending, nobody else can come along and try to run that same gift card somewhere, okay? And as a mechanism, it's applicable to both data rows, which respond to particular objects. So when Ticketmaster has its list of tickets, those are all rows in a database table, right? So the table could be particular concert, and for every concert, there's a section, there's rows, whatever, but each record would be a particular seat that gets ultimately associated with a particular buyer. So those rows would be locked. Or particular fields could be locked. You could say, well, I'm making some change throughout the database table, I'm going to lock that entire field. But either way, right, you might have to lock part or the entire table. So basic practical problems. Number one, how long should a lock last? And on Amazon, I don't know, it's not infinite, but it tends to be a few days or a week, and I haven't done an exhaustive comparison about this, but it makes sense that for some items it would be longer than others, right? And at different times of the year it would be longer than others. So, for example, if it's a hot toy and it's the Christmas season, then that's the sort of thing the lock probably doesn't last very long, right? If you leave the Amazon site or it's been like longer than half an hour, Amazon might just drop that from your cart. Okay, but I have had it seen where I've added stuff to my cart at Amazon, been away for a few days, come back like 5 days later, and the stuff is still in my cart. So again, haven't done an exhaustive check on this, but certainly it could be a few days on Amazon. Something like Ticketmaster, right? We know every stage of the process, there's only a few minutes delay. You got to pull the trigger or not. Next question. How many things can a single user lock, right? This is the sort of thing that you want to prevent. You don't want somebody to go to Amazon and literally add every product in Amazon to their cart, right? That would be a problem. Nobody else could buy stuff. You don't want somebody to be able to do like a giant lock like that. And there's a couple other problems, Deadlock and Livelock. So we've talked about Deadlock. We can talk about Livelock too. All right, so the idea with Deadlock is simply that two database actions block each other. And in a well-designed database, there will be mechanisms to prevent this from happening. But the point is you have to develop those mechanisms to prevent it. But the basic idea is this. Suppose you have two database updates, you're changing something, and they're trying to do an update to two tables, right, to two rows in the same table. And this is the example we did before, but I'll just do a quick rerun. Okay? So let me see, line it up with the actual letters I'm using. A and B. Okay. And suppose there's two operations, U and V. So, operation U attempts to update A, then B, and the way it goes for V is in the opposite direction, right? So, attempts to update B, then A. So, when U tries to update A, it goes to A and say, okay, this is fine, nothing's going on with A, great, I will make the update. B, likewise, starts to update B. Does the update, right? B is open, it can do anything, so yeah, okay, do it. And then they both wait to update the other one, but guess what? Both of those things are locked, right? A is locked because U has updated it but still wants to do B. V has locked up B though, so they're both just waiting for each other to finish. It's a deadlock because nothing is happening. They're just kind of standing there staring at each other saying, when are you going to be done? Okay, and eventually the attempted operation will time out, but that could be a while, and in the meantime, the transactions aren't going through. Okay, so that's an example of deadlock. Livelock, on the other hand, Livelock is a little bit weirder. So I'll give you a non-database example first. You ever walk down a narrow hallway and you're walking on the same side as somebody else, right? So you're walking on your right, they're walking on their left. You get up to each other and then you're like, one of us has got to move. So what happens? You both take a step to the side, right? And you're still facing each other. And you're like, oh shit, what do we do now? So you step back. But you both have the same thought at the same time, and you both step back and you're both still blocking each other, right? Everybody's done this at least once in their lives? Yeah, that's Livelock. Things are still moving, but the system is still locked. Yeah? That's Livelock. Okay, now an example of how this might happen in a database, right? So the idea is trying to resolve the deadlock, in fact, actually perpetuates it. So, simple example of how deadlock might turn into Livelock in this case, I use blue. Livelock could happen if, in response to a blocking situation, both U and V abort the initial operation and attempt it again with the sequence reversed. Okay? If your database says, if you find it blocked, then don't do it. Reverse the order of the things you were going to do, and then try again. Okay? What would happen? Of course, U would update B, V would update A, and they'd still be waiting for the other one to do it. And guess what? When they found they were blocked again, they'd attempt to reverse it back to the original state, and they'd still be blocked. Okay? So again, in a well-designed system, this shouldn't happen, but not all systems are always well-designed. So, and in any event, they need mechanisms to prevent this. Another possibility that could happen is if both U and V, when they recognize a blocking situation, they cancel the operation, they pause, they wait exactly 1 second, right? They wait the exact same time, and then come back to the system again to try to do the change. But guess what? If they're both coming back in the same time, system's still going to be blocked. Okay, nothing's going to have changed. Okay. All right. So is that good? Any questions on any of this stuff thus far? Yes?
So what happens in a deadlock? Does the database have to wait for an administrative override?
Well, I mean, it depends on the database. The most common thing is if you have two operations that are trying to do something, if after a certain time they can't, then the operation timeout, and you get some notification, database operation failed due to timeout. Okay, but any system is free to set whatever timeout it thinks is appropriate, or it's free to not have a timeout, which is usually a bad idea, but you could set that in. You could just say, no, you guys just actually stare at each other all day, okay, until somebody pulls the plug on the system. It's system specific. Yeah, but typically you'd have a timeout. Okay, good. So now, this is where we get into the important thing, okay, transaction structure. So, Transactions in this kind of big system, any system really, follow some kind of request and agreement sequence. Basically, you ask the system to do something, and the system confirms that it's able to do it and has done it. So, for example, user requests to add a product to a cart, right? You say, you click the cart button, add it onto your cart, great. And the system agrees to it or not, right? Because what could happen, again, there could only be one thing left, and in the window between when you click it and when the system checks to see if the thing is available, it might not be available at that instant, right? So the system's going to have to agree, okay, yeah, there's still one left, and then we can add that to your cart. Okay, eventually, you add all the things to your cart you go to checkout, the transaction will either happen or not, okay? And we'll get more detail, but that's the idea. You ask the system to do something, system checks if it's feasible. If it is, yeah, it goes through. Okay, now of course, not always just within Amazon, right? Not always just within the two parties. Sometimes you have to do checks out to other people. For example, credit card checks. You have to verify if the transaction is okay. That's probably not going to happen under Amazon's roof. Now, in a well-designed system, any final changes to the data get deferred until everybody involved has agreed to the transaction, right? Because what you don't want to do is have to go back and reverse something that's already done. So essentially, you write down a bunch of changes on paper, and once everybody has agreed to, yeah, this is what we're going to do, right? All the systems involved with that step in the transaction, once everybody agrees that it's going to happen, then you make the changes to the database. Okay, so basic problems, all right, here's a couple things. So, for example, in banking, typically customers are isolated from each other, right? It is possible that two people could have simultaneous access to the same data. For example, two users of a shared account or multiple ATM cards, multiple debit cards using an ATM for the same account. It's possible, it can happen, but it's unusual. Most of the time, most customers are looking at their data and only their data. So that's a little bit different. So simultaneous access is low, but it's possible. System still has to look for it. Retail, though, it's very typical that multiple people have access to the same data, right? Think about Amazon. There's a product page. If it's a popular product, there could be thousands of people or tens of thousands of people looking at it at the same time. Simultaneous access to data is absolutely routine for retail, okay? So if something goes wrong with simultaneous access for banking, it is potentially very damaging, again, like the Bitcoin hack. So they got to watch for it. But most of the time it's not going to happen. And so they can put, fairly strict controls on that to make sure it doesn't. Because number one, the damage is potentially high. And number two, doesn't happen that often. Not going to affect that many users. Retail, yeah, they kind of got to expect it. So this all falls under the heading of what's called concurrency, right? So concurrency or concurrent access is basically when people have access to different people have access to the same data at the same time. That's concurrent access. So what happens? Well, there's a few different policies that a system could adopt. Number one, it could absolutely refuse to allow anyone simultaneous access to the same data. Okay, so in some cases this may make sense. If you say, for example, it's financial stuff, you say, well, you can only look at this if nobody else is looking at it. Or, for example, if you're making changes to a document, you might say, okay, you are the person who is looking at this document, and we're going to treat it like a library book. While you have access to it, nobody else can use it. Okay? That's one possibility. And for some models, that works. Again, for example, if you have software licensing, if your enterprise has only paid for one license of a copy of software, then you're only going to have one, right? And so only one person can use it at a time. And in that sense, only one person has access to that data at a time. Other possibilities, you might allow any number of users to read the data. Anybody can look at it. So, for example, for a retail page, this is pretty typical. You allow an unlimited number, basically, of users to look at the same product page. Okay? But then you have to some extent, guard against these kind of dirty reads. So one possibility is you say, no changes are permitted if there's more than one viewer, right? So if you have multiple people looking at it, you can't have anybody change it because then that could potentially result in dirty reads. And that might be something that's feasible, again, if you can lock out viewers. But for something like a product page, that's not, right? You don't want to have 10,000 people looking at a product page and then say, oh, since you're all looking at it, nobody can actually buy anything, right? That would be what you definitely don't want. So For product pages, they typically do something like allowing changes, right? Allowing you to add a product to the cart if there's more than one viewer. But as far as possible, those changes get immediately echoed to everybody else looking at the page. And that's what happens if you go to Amazon, you add something to your cart. If there's a bunch of people looking at it and they have, only 5 in stock by now, then that goes down to 4 in stock, and that gets echoed to everybody else in the world who's looking at that web page. Okay? Now, what drives it? Well, a lot of things. How many users you are, how likely it is that there's going to be simultaneous access, how complex the system is, right? Basically, how much of a hassle it is to do that. And the big one, though, is the importance of data integrity versus response time. So, data integrity means the data is what you think it is, essentially, right? So, in this case, it would be everybody who's using the system at the same time sees the same data that's actually stored in the back end. Okay? Versus response time. Okay. Bitcoin, data integrity is hugely important because if somebody does a transaction on one pile of Bitcoin, right, it's digital, can happen very fast. Data integrity is big, right? That's a lot of money that could be going out the door. Response time, on the other hand, not as important. I mean, yeah, you'd like the system to be fast, but in the choice between having transactions take a few seconds versus having somebody hack your system and like having millions go out, right? Data integrity is obviously far more important. In the case of Amazon's web page, right, they're selling butt heads on some product page. Response time is really important, right? You want people to go to the site and have the site run fast. Data integrity in that particular thing about the number still in stock, not that important, right? You would much rather have your site run in milliseconds and allow that there's an occasional little discrepancy between the number of things in stock and what people actually see. I'll give you another example. YouTube. Okay? So what? Give me a popular video. Popular song.
No guidance.
Okay, well, all right, I'll accept that. Let's see. No guidance. That's fine. Okay, so you see this has 105 million views. Okay, so if I look down here, you see the number, whatever, 105,880,769. Okay, we'll give the video like a minute. She's trying too hard. Okay. They'll be done in a second. Okay. No thanks. So we play it, right? And that counts as a view. That counts as somebody looking at it. If I go and I reload it again, the page count, the view count remains the same. Reason is, the damage of having a slight discrepancy in the view count, nobody cares, right? Oh, well, Chris Brown is going to come and say, hey, YouTube, you didn't update it when Professor Doug came and watched my video, right? You didn't update it in real time. Nobody cares. The damage by that is trivial. What we really want is response time that everybody who's watching the video can see it quickly. YouTube does track this. They will get around to updating it. Like, if I did this for a minute, eventually you'd see a change, right? But if I just do it like one at a time, no, you're not going to see that change. Okay? So that's another example. Data integrity in that sense is not very important. Having an absolute precise view count, who cares, right? Response time is what matters. Okay. We'll talk more about that in the YouTube section. Okay. A couple other things. Atomicity. So, in this context, atomicity again means group of related tasks is entirely completed or not at all, right? Basically the same as the acid property. So, you have a group of related transactions. For example, I am trying to buy some stuff on Amazon. If something goes wrong with it, the credit card gets declined, none of the other related things happen, right? The goods don't get sold, the inventory doesn't get reduced, no payment gets processed, right? You want everything to line up. Either the process happens, the payment goes through, and then all those things happen, or the payment doesn't go through, and none of them happen. That's atomicity. The transaction is treated as a unit. Isolation, again, basically means the same thing as in the acid property. Restrictions that are placed on access to data. So the practical way that this is implemented any intermediate stages of the transaction don't get seen by the outside. So if the transaction is atomic, nobody sees that intermediate stage where perhaps it shows that the credit card transaction has gone through, but the inventory deduction hasn't happened, right? So all those changes, they're happening on paper, but nobody can look into the system, right? No other user can come along and check what's going on. I can't create a duplicate copy of myself on another site and go in and look at it. Nobody else gets to peek in there and see those transactions while they're still processing. So anybody who's looking at it either sees the initial state where the transaction hasn't happened yet or the final state where the transaction has happened. They don't see a state where some parts of the transaction have happened and others haven't. And that protects against the interleaving of data, like the interleaving of data operations like with the ACID properties. Now in practice though, this operates as a trade-off with concurrency because you want to allow concurrent access, makes your system easier to use, right? You can support many simultaneous users. But if you allow concurrent access to data, in some sense you have to be giving up isolation because there's the possibility that those users could be looking at the same stuff and could mess up the system that way. Okay. Now, generally, database records get locked to prevent overlapping operations. That's a standard technique. You have some governing mechanism up above, and it says, oh, this database operation is looking at these tables, these rows, so nobody else can do anything to change those tables and rows until that operation is done, right? So, transaction process starts, the relevant records become unavailable to other processes, okay? And after the transaction succeeds or fails, the lock gets removed. So basically you're saying somebody else is using this data, you can't, a second person can't come along and look at and try to manipulate that same data. That's how you implement the ACID properties. However, problem happens if you have a high volume or data intensive situation, the system can get locked up. For example, if you have many processes accessing the same data, right? So if you have a bunch of users who simultaneously want to make a change, right? They all want to buy one copy of the same product. Think about that. If Amazon has like 10,000 buttheads in stock and you simultaneously have 10,000 users that all want to buy that, what's going to happen? Well, they're going to basically create a long queue. The 10,000th person is going to have to wait for those other 9,999 processes to finish before he gets his turn, okay? Or you can have one process accessing a very large amount of data. Imagine if somebody does a query or some operation that affects multiple tables and large number of rows within those tables, then your governing system is basically going to say, you're doing this big operation, nobody else can access these tables while that's going through. Imagine if you're doing one of those big queries that takes a really long time to go through, and you say, okay, nobody else can write to this while this big long query is running through. So basically your database kind of gets locked up for a while. This is the problem. So locking is good. Locking will ensure that everybody gets the correct answer, but when you're at scale, locking can make it happen so that it takes a really, really, really long time to get that answer. So there's kind of a trade-off. And that's where balancing concurrency and isolation come in, right? So isolation, you ensure that data integrity is great, but it limits scalability. You can't run a big high-volume system if you strictly enforce isolation. On the other hand, allowing concurrent access means your database is going to be less accurate. So what do you do? Well, in fact, there is no solution. There's no magic bullet that says, I am going to provide isolation and concurrency. You can't. You provide one, you give up the other. There's only options around what could go wrong. Now, Oracle, which is one of the big relational database providers, they do have different isolation levels. Like if you're like a database tech guy, you know this stuff, but if you're not a database guy, yeah, you're not really going to get it. Okay, but there is a link, you can check out some of that. But boil it down to best practice. Strict isolation for high value transactions, right? If you're doing a wire transfer of $3 million from your bank, the bank wants to make sure that nobody else is, doing $100 $3 million wire transfers from that same account, right? You want to make sure that that is handled very strictly in isolation. But allow concurrent access when the potential losses are small, right? And again, there's a link to that Poloniex exchange hack if you want to recap that, but we've seen it before. Okay. Rollbacks. Rollbacks are a mechanism for recovering from uncompleted transactions. For example, for whatever reason something goes wrong, right? Invalid parameter, say the credit card is maxed out, or some component failure, right? There's a hardware thing, or there's a software failure, or whatever. Transaction doesn't go through. So the basic method where rollbacks work, number one, the system keeps a file of all transactions that have started but haven't finished. Basically all data changes to the database that have started but not finished, and tracks their initial state. So if a failure happens, right, basically by reversing all those operations, the system can be returned to its last, good state by unraveling all that. So clearly, it is vitally important to maintain the integrity of your rollback records, because stuff does go wrong, and the bigger the system is, the more likely it is that in any given instant a piece of hardware goes down, or some software failure. Okay. So that's essentially what a rollback is. You keep track of what's happened so that if there's a failure, you can restore the system to its original good state. Okay. Very quickly, we're going to cover two-phase commit. We'll quickly recap it. This is the important thing of the lecture, so we'll get it. Okay. So, basic problem. Suppose we have two or more linked databases, and we want to make sure that they have the same data values after a transaction, right? So, for example, customer makes a bank withdrawal using an ATM. Afterwards, you need to make sure that what's on the ATM interface matches what's in the back-end database. Okay? And similarly, secondary transactions throughout the enterprise. So whatever notifications have to go out through the bank that their reserves have gone down a little bit, or maybe they need to send out a truck to refill the ATM, stuff like that has to line up as well. So there's two correct outcomes. Number one, either the customer gets the money, the back office back office accounts gets updated, or the customer doesn't get the money and all the data in the back office doesn't get updated, right? Either of those are correct outcomes. They're correct in the sense that there was a change and the change is reflected through the whole system, or there was no change and so there's no change throughout the whole system. Yeah? Okay. So this two-phase commit, and I am going to walk through this, and we'll come back and do it again very briefly on Mondays to start, because otherwise people are going to forget. I'm going to blow this up. Boom. Okay. So we have a few things. We have a transaction coordinator. That's basically Amazon. Okay, Amazon's interface, coordinator, whatever. These resource managers are basically individual system databases. Okay? And then there's me. I'm over here. Me, and I buy stuff. Okay? So I'm buying some stuff at Amazon. So what happens, the basic process is this. I tell Amazon what I want to buy. Amazon tells all the related databases to prepare. So it says, TC, Transaction Coordinator, tells all RMs of upcoming database operation. Okay? It says, this is what we're going to do, this is what you need to do. Okay? Individual resource managers pencil in the changes, right? That's not a literal thing, but it's an easy way to describe what's going on. They're making changes, but they haven't been finalized in the database. So, pencil in changes to their respective databases. Okay, so all the resource managers, they say, oh, this is what we need to do, right? So if it's inventory management, they're going to pencil in that one thing is deducted. If it's a credit card, the credit card system is going to pencil in that the money's been deducted. If it's FedEx, they're going to say, FedEx is saying, okay, we're going to pencil in that we need to have space for this new item on a truck. All those sort of things happen, okay? When done, resource managers tell TC they are ready. Okay? They say, okay, we've penciled in the changes. They haven't actually changed anything yet. They say, we know what we're all supposed to do. We've all verified that this operation is feasible. At that point, TC knows that, oh, I should add here, and prepare rollback records. Okay? So they also, the resource managers, whatever they need to do for their individual rollback records, they also do that. So at that point, when everybody's confirmed back they're prepared, the TC knows that all RMs can do the operation and can recover from a failure. Okay, so if something goes wrong, that's okay too, because they've all confirmed back that they're prepared, so they know that they have the rollback records in place. Okay, so in the commit phase, TC tells RMs to finalize the changes. Say, okay, do it, everybody. We're good. We can do this. Okay? The resource managers, one by one, actually finalize the changes and inform the transaction coordinator. So all our RMs do this. At the end, TC knows all RMs have finalized the transaction, thus all DBs are correct, are updated. Okay, that's the essential there. So, quick recap and then I'll cut you loose. I buy something, there's a transaction coordinator at Amazon. Amazon tells everybody, hey, this is what we're going to do. All you resource managers do it. The individual resource managers, they pencil in the changes. Then they also prepare rollback records. When they're done with that, they tell the transaction coordinator that they are prepared. That's the end of the prepare phase. At the end of the prepare phase, the transaction coordinator knows that everybody's good to go. In the commit phase, the transaction coordinator says, okay, now commit. Now finalize the changes. The resource managers, one at a time, they do that. They confirm back to the transaction coordinator that it's done. At the end, once the transaction coordinator has heard from everybody, it knows that the operation is done. Okay? Now, if anybody's still here, I'll very quickly just do this thing if it takes a second. Just to give you an idea, this is how much text I'm saving you. Okay? This is a description of two-phase commit that I've distilled down to one image and 5 sentences. So, just saying, you're welcome. All right, we'll see you next week.